Hello, my name is Jakob Python. Today I'll present my work on design frameworks for polarization insensitive multifunctional achromatic metalenses. One of the reasons why this topic is interesting is, as you may know, there's an increasing demand emerging for lenses. You probably all remember when your phone used to have one camera. Now it might have 3 or even 5. This puts a certain limit on what we can do, because classical optical components are inherently bulky, especially when trying to suppress aberrations. As an example is this patent from Apple, where they used 3 different polymers in various complex shapes with the goal of suppressing aberrations, especially chromatic aberrations here. They occur because light at different wavelengths are focused at different positions. As you see, this lens is 4.6 millimeters thick, meaning that one of the limits of your phone's thickness is its lens system. Furthermore, designing and making these systems is also complex and expensive, and it affects other things as well, such as microscopy, lithography. Therefore, there's a great desire to miniaturize these components. Miniaturization can be achieved using metasurfaces, as first discussed by Nanophotonics and collaborators. Using sub-wavelength nanostructures, like gold rods in this case, light can be tailored and we can control the amplitude, the wave number, the phase, and the polarization. This enables us to do virtually everything. For example, we can create holograms, polarization elements, and as we'll discuss here, metalenses. Achromatic metalenses have already been investigated a lot. Here are some of the examples of polarization and sensitive lenses, where light is focused achromatically. This is in the visible and this is in the telecom ranges. However, as you may notice, there's these parasitic focal spots that occur. This means that the efficiency is inherently limited of these devices. These parasitic focal spots can be removed by disentangling the phase from the dispersion, which we can also call group delay. This disentanglement has so far been achieved by using polarized light and the concept of geometric phase, and then rotating these structures. In this work, we focused on the mid-infrared range, since it at the time of writing was rather unexplored with respect to lens design. We wanted to make a lens working in transmission mode and being polarization insensitive without it causing parasitic focal spots. To do this, we wanted to create a general framework that could be used in all spectra, and we want to show that our framework is multifunctional. To do this metalens design, we first have to see what it actually requires to make an achromatic metalens. For lens, the phase at any given position and frequency is related to those 2 components and the desired focal length, f. This, however, means that the phase of any metalens at any position varies a lot with respect to the frequency, as you can see in the image. Additionally, since phase is relative, we can also add a frequency-dependent constant, c omega, for our design framework, which we do here. Previous design methods have used, for example, particle swarm method to fit meta elements to the phase curves and to fit c omega. Other works have tried to define c omega based on their lens requirements. Both methods are valid and works okay, but not perfectly, since the lens size and focal length is defined before fitting the curves. The last method also says that the phase for all wavelengths should be 0 at the edge of the lens. In this work, we used hexagonal silicon pillars. Some were solid, some with a hole in the middle, and some were shaped like a star. These element designs allow for polarization and sensitiveness. By sweeping the geometrical parameters of these meta-elements, we can establish a library of meta-elements, with the solid ones defining the upper boundary. What we see is that the group delay is positive for all values, and we'll come back to why that is important soon. We also found that the elements have quite linear dispersion, make them easy to fit. And also, the library is essentially repeatable with respect to phase for every 2 pi. With our library in hand, we can now turn to designing a metalens. And to do this, we have to redefine C omega. To find this value, we first noticed that this meta element library has a certain shape. And this shape, we can define the largest phase difference within it. This is the red line. This red line and where it intersects with the edges of the library yields the theoretically perfect value of C omega, this one. And we simply need to pick meta elements that lie on this red line for our design. With our design methodology in hand, we create 2 lenses, one where the original library is used, and one where it is extended to allow for 2 pi repetition. We call this the A-type and the B-type respectively. We keep the focal length fixed, allowing for the B-type lens to be larger. By focusing a pulse and pinching on the lenses, we can see how they focus a specific wavefront. We can see that the pulse arrives slightly later for the B-type lens because it is larger. But we also see a slight elongation of it. We attribute this to 2 reasons. First, we have an abrupt phase jump in the B-type lens system. This could cause irregularities in the wavefront. Second, the meta elements from the extended part of the library, we found that these exhibit less ideal wave transmission behavior due to the excitation of higher order modes. It is, however, not particularly strong. However, these things should be considered if designing meta lenses for pulse beams. Having checked how the wavefront is focused, we can now turn to verify the achromatic nature of the meta lenses. Clearly, light is focused well at the intended focal spots for the whole 2.5 micrometer bandwidth that we pick. And it would even look like it could focus well for an even wider bandwidth. Moreover, we don't observe any parasitic focal spots, even though we use a polarization insensitive meta lens. This is attributed to our choice of C omega. For the B-type lens, we also see a slightly smaller focal spot. That is because the numerical aperture of the lens is larger, because the lens is larger. To characterize our lenses better, we can look at some figures of merit. First, the focal length shift. It is less than 10%, indicating a good suppression of chromatic aberrations. This is also highlighted by looking at the shaded area, which is the range of the depth of field. Additionally, both lenses display a nearly ideal full width at half maximum value, close to the theoretical diffraction limit. And this remarkable localization of field of power at the desired focal spot leads to a focusing efficiency average of 41% over the entire bandwidth for both lenses, with a maximum efficiency of 54%. Additionally, our design methodology allows for the generation of broadband-focused vortex beams with polarization independence. In order to do so, the meta surface should incorporate the phase profile of a meta lens and a Q plate together. Here, L is the topological charge and theta is the azimuthal coordinate. That is a Q plate. In our framework, this equals a 2 pi broadening of the red phase line. Here we show a meta lens with a topological charge of -1. Again, we see that chromatic aberrations are significantly reduced. And we see at the focal point, the cross-sectional intensity profile reveals the characteristic donut shape of vortex beams that indicates a singularity in the center. We also combine the electric field components with a linear phase ramp. This is similar to performing an interference experiment in practice. And fork dislocations are observed. These verifies the phase singularity. So, to conclude, we developed an analytical framework for achromatic metalens design we prescribe the exact phase range and appropriate spectral degree of freedom. The framework can be extended to allow for vortex-generating metalenses, and this framework has clarified fundamental physics involved in chromatic aberration correction. If you would like to know more, then please have a look at our paper or contact us. Thank you very much.